In this video we're going to be revising periodic trends. So periodic trends is a topic where you have to know various trends across period 3. They're both the trend and the reason for them. So the first one is the trend in electronegativity, the trend in ionization energy, trend in atomic radius, and the trend in melting point and boiling point. The trend and the reason for which both the same for melting and boiling point. So period 3 is this one here, sodium to argon, and that's what the spec focuses on for Chem 1. So the electronegativity, if you remember, is the power of an atom to draw electrons towards itself in a covalent bond. Now the fact electronegativity is defined as in a covalent bond, we know that argon doesn't really have electronegativity, so we're going to cross that one out in this trend. You also know from lessons that electronegativity increases as you go across the period from left to right. And that's no different for period 3, so we know that it increases, but why does it increase? So electronegativity depends on two things. Firstly, the number of protons in the nucleus, and secondly, where the electrons are in relation to the nucleus. So we know that the nucleus, as you go from left to right across any period, will have more and more protons as you go across. So that means the nuclear charge of the nucleus increases. So that's the first reason that the electronegativity increases across period 3. Nuclear charge increases. The other reason is that as you go across the period, the extra electron that the atoms gain does not go in a shell further away from the nucleus. So, for example, sodium, it will go there. For magnesium, it will go in the same shell. For aluminium, it will go in the same shell, and so on. So that means that the electrons aren't getting any further away from the nucleus, and also there is no extra shielding from electrons that may be further in. So the other two reasons are that electrons are in the same shell, which means that they are the same distance away as the other electrons, and there is no extra shielding. If we now move on to the trend in ionization energy across period 3, we know that there's a general trend as we go across that the ionization energy generally increases. Now this is covered in a different video as well, but I'm going to cover it in this one quickly. So it generally increases, and again that's because of the same reasons really as why the electronegativity increases. We've got nuclear charge increasing, the electrons enter the same shell, so they're the same distance away from the nucleus. Now the reason why I said that the ionization energy generally increases because there are two exceptions to this rule. The first one is aluminium. Now when we describe why there are exceptions to this rule, we've got to first state where the electron is compared to the last element. So we're comparing aluminium to magnesium here. So the electron in aluminium is in the 3p orbital rather than the 3s orbital, which is where the actual electron is in magnesium. So electron is in 3p orbital. So that's the first thing we do, we just state where the electron is. The next bit of the answer will state why that affects the ionization energy. So we'd say 3p is further away from the nucleus than the 3s, which is where the actual electron is in magnesium. And the last thing we say is that therefore the electron requires less energy to remove. And that's how you'll go through, that's the process you'll go through for any question that asks you to compare two ionization energies of two elements. So if we do the same for the other exception, and that is sulfur, so we know again that the outer electron for sulfur is in a 3p orbital. So electron is in 3p orbital. Now, the electron in phosphorus, which is next to sulfur, is also in a 3p orbital. So why is this one different? Well, as we know, as we fill up the p orbitals, aluminium will just have one electron in the p orbitals. Silicon's going to have two, but the next electron is going to go in the one next to it. Phosphorus is going to have three, and then sulfur has four, which means that the fourth one is paired with another electron. So outer electron is now paired. And then you say why that makes the electron easy to remove. You say added repulsion between electrons means electron requires less energy to remove. The next trend you've got to describe is the atomic radius, which is the distance from the nucleus to the outer electron. And as you go across from the left to the right of the period, this time the atomic radius decreases. But the reason is exactly the same as the others, the ionization energy and electronegativity. You'd say the nuclear charge increases, and electrons in same shell and no extra shielding. So the fact the electrons aren't getting any further away in terms of shells means the nuclear charge pulls those electrons further in as it gets stronger. And so that means as the electrons are getting pulled further in, the atomic radius, i.e. the distance from the nucleus to the outer electron, is decreasing as you go across period 3. Now the trend in melting point or boiling point across period 3 is a bit more complicated because there's not just a general trend across the period. The period is split into distinct sections where there are mini trends, if you like, and the mini trends are based on the different crystal structures that those different sections have. So the first section is between sodium and aluminium, which all are metals. Silicon is by itself, and then the last section is from phosphorus to argon, which are all molecular compounds. And what you find is that we have sodium increasing to magnesium, increasing to aluminium, which will then increase sharply to silicon, and then phosphorus will drop down below sodium and magnesium as well. Sulfur goes back up again, chlorine goes down, and argon goes down as well. So there's no real trend, but you can describe why these changes happen if you look at the structures of all the different elements. So you look at the first mini trends, the sodium to magnesium to aluminium, we get an increase in melting point as we go across from sodium to aluminium. So all three of these elements are metallic, and that's the first thing that you would write in an answer, that all three of them are metallic. And then you've got to think, well, why would metallic bonding get stronger? And there's two reasons. The first is looking at the nuclear charge. So remember that the metallic crystal structure is a lattice of positively charged metal ions that are then surrounded by a sea of delocalized electrons. So if either the charge on the metal ion is greater or the number of electrons that are holding it together are greater, then the metallic bonding will be stronger as well and therefore have a higher melting point. So as you go across from sodium to magnesium to aluminium, the nuclear charge increases. Sodium always makes 1 plus ions, magnesium makes 2 plus ions, and aluminium makes 3 plus ions. So you can see the nuclear charge is increasing, or the charge on the ions is increasing. Also, if sodium is a 1+ ion, that means that's only releasing 1 electron into this delocalized C, if you like. If magnesium is 2+, that's releasing 2 electrons each, and aluminium is 3+, that's releasing 3 electrons per ion. So as you go across from sodium, magnesium to aluminium, not only is the charge on the ions increasing, but also the number of delocalized electrons in that C is also increasing. So that's the other reason for the melting point increasing. Now you may get asked to compare two of these rather than just describe the trend. So if you were comparing magnesium to aluminium, you'd say that aluminium has a higher charge in its ions and also has more delocalized electrons in its structure, and therefore metallic bonds are stronger, which means it needs a higher temperature to melt it. If we now look at silicon, which is really by itself, you'll see that the melting point of aluminium to silicon jumps up, and then from silicon to phosphorus goes right back down again. And that's again because of its crystal structure. So aluminium is metallic. Phosphorus is molecular. But silicon is giant covalent, which means that its structure is made up of entirely covalent bonds, or all the atoms are joined by covalent bonds, which means if you want to if you want to melt silicon, then you have to break every single one of those covalent bonds in its structure. Silicon has a very similar structure to diamond. So if you're describing why it has such a high melting point, you would say that to melt silicon, you have to break many, which is a key word in this answer, many strong covalent bonds. And that's not the same for aluminium or phosphorus. Phosphorus, you're only breaking weak van der Waals forces, and aluminium breaking metallic bonds, which aren't as strong as those covalent bonds. So the final mini trend we have to describe is the melting points between phosphorus and argon. What we find is that phosphorus has a lower melting point than sulfur, but sulfur has a higher melting point than chlorine, and chlorine has a higher melting point than argon. The reason for any melting point is always down to its crystal structure, and these all have a molecular crystal structure, which means all we have to break to melt these are the intermolecular forces between the molecules of the elements. So all the intermolecular forces between all these molecules, they all only have van der Waals forces. The reason for that is that there is going to be no difference in electronegativity between same atoms. So that means they're not going to be the bonds aren't going to be polar, which means they can't have permanent dipole-dipole forces. There can't be hydrogen bonds because there's no hydrogen in the molecules. So all that's left is van der Waals forces, which are very weak. But van der Waals forces also differ in strength between different molecules, and there's two reasons for that. One, if there's a difference in surface area, and two, if there's a difference in number of electrons in the structure. So we've got to look at what molecules these elements form. So phosphorus forms P4 molecules, i.e. 4 phosphorus atoms in a molecule. Sulfur forms S8. Chlorine forms Cl2, and argon just is by themselves, they don't form any molecules. So you can see that sulfur will have the biggest surface area, followed by phosphorus, followed by chlorine, followed by argon, which is precisely what the order in which the melting points are in this series. So S8 has highest, or rather biggest surface area, and therefore highest melting point. Sulfur, because it's got 8 atoms in its molecule, will also have more electrons in the structure, and that will also give it stronger van der Waals forces, but the main reason for these differences in melting points is their surface areas. So if you need to remember these structures, the fact that sulfur is S8, phosphorus is P4, chlorine Cl2, and argon's just by itself. And sometimes you'll be asked to compare two of these, you may be asked to compare phosphorus and chlorine, in which case you would state that they were molecular, then you would state that they're held together by van der Waals forces, then you would say why the van der Waals forces were stronger in phosphorus than chlorine, and you'd say the reason for that is that phosphorus is P4, or goes around as P4 molecules, chlorine goes around as Cl2 molecules, and therefore phosphorus has a higher or bigger surface area than chlorine does, and therefore has stronger van der Waals forces.